the second part of our Chapter 12 Standard Functions. The objectives of this session are: find the extremum, absolute or relative of a function defined algebraically or graphically, set up the table of variations of a function defined algebraically or graphically. Please prepare the following materials and let's start. Maximum and minimum of a function. The absolute maximum and absolute minimum. In the adjacent figure, consider f a function and let C be its representative curve over its domain of definition df. Notice that the smallest value of f over its domain of definition is f of alpha. This is the lowest point on the curve. And the greatest value is f of beta, the highest point on the curve. So we say that f has a minimum of f of alpha at x equal alpha and a maximum f of beta at x equal beta. By definition, f has a minimum at the real number alpha of its domain of definition if and only if f of x is greater than or equal to f of alpha for all x belonging to the domain of definition, which means that f of alpha is the minimum if any other value on the curve is greater than f of alpha. So it's definitely going to be the minimum. The same for the maximum. F has a maximum at the real number beta of its domain of definition if and only if f of x is less than or the other values of f of x are less than or equal to f of beta, since f of beta is the highest or the greatest value. Maximum and minimum, some remarks. F of alpha and f of beta are sometimes called absolute minimum and absolute maximum. They are the absolute minimum and maximum when we're talking about the whole curve. This is the lowest point on the curve and this is the highest point on the curve. We are going to see the relative minimum and the relative maximum in the coming slides. A maximum or a minimum of a function is called extremum. So f of alpha is an extremum and f of beta is an extremum. Example 1. Consider the function f defined on R by f of x equal x squared minus 2x plus 3. First, we have to show that f of x is equal to x minus 1 squared plus 2. So we have to expand this expression to obtain f of x. Second, we have to deduce the absolute minimum of f. So here we have f of x. We use the second form of f and we move 2 to the other side. Why? Because I can determine the sign of x minus 1 squared. It's always greater than or equal to 0. So f of x minus 2 is always greater than or equal to 0. F of x is greater than or equal to 2. Once I determine that f of x is greater than or equal to a constant number, I can therefore determine the absolute minimum of f, which is 2. Since whatever was the value of x, f of x is going to be greater than or equal to 2. So 2 is the minimum value of f. Determine the abscissa of this minimum value. No, 2 is the minimum, so 2 is the ordinate of the point representing the minimum. To find the abscissa of the minimum, we should solve the equation f of x equal to in order to find x. So it's x minus 1 squared plus 2 equal 2, and hence x is equal to 1. Therefore, f attains its minimum value at x equal 1. Example 2. Consider the function f defined on R by its representative curve C as shown in the adjacent figure. So the first example was concerning a function defined algebraically. Now this is an example concerning a function defined graphically. Does f have an absolute maximum? Look, f comes from plus infinity, it decreases to attain 1, then it increases and continues to plus infinity. So no, the function has no absolute maximum. Since it doesn't have a greatest value, plus infinity, it's not a well-determined value. In fact, the upper bounds of C doesn't stop at a given real number. They approach to plus infinity. Now, does f have an absolute minimum? Yes, the absolute minimum is 1. Application 1, please stop the video and try to solve the application. Relative maximum. The function f in the adjacent figure has on the interval a0 a relative maximum at a, because for every x belonging to a0, f of x will be less than or equal to f of a. Relative minimum. The function f in the adjacent figure has on the interval cb a relative minimum at c. This is the function on the interval cb, and this is the lowest point at c, so it's f of c, because for every x belonging to cb, f of x is greater than or equal to f of c. So a relative maximum or a relative minimum is a maximum or minimum, but on a defined interval, on a part of the domain of definition of the function. Example 3, consider a function f defined on 0, 3, this is the function, by its representative curve. Determine the relative minimum of f on 0, 1. This is the interval 0, 1. This is the curve on 0, 1. The relative minimum is here, so it's 1. Determine the relative maximum of f on 2, 3. This is the interval 2, 3, and this is the curve on the interval 2, 3. The maximum, the relative maximum is 1. Determine the absolute maximum of f. This is f. Where's the highest point on f? It's here. What is the absolute maximum? It's 2. Now notice that in the parts 3 and 4 we don't have intervals, because the absolute maximum and the absolute minimum are the maximum and minimum on the domain of definition, which is 0, 3. Now, determine the absolute minimum of f. The absolute minimum is minus 2. Application 2, please stop the video and try to solve the application. Now, the second objective of this session is the table of variations. The curve C at right is the representative curve of a function f defined on R in an orthonormal system. Now f is strictly increasing on minus infinity, minus 1. So on the table of variations, it's illustrated by an arrow that is moving upward. And f is strictly decreasing on the interval minus 1, 1. So on the table of variations, it's illustrated by an arrow that is moving downward. And finally, f is increasing on 1 plus infinity, and on the table of variations, it's illustrated by an arrow that is moving upward. Now, how to draw the table of variations? First, on the first line, we put x, and on the second line, we put f of x. What are the values that you have to put here? Minus infinity and plus infinity, which are the bounds of the domain of definition, and the abscissas of the extremum of this function. This function admits a maximum at x equal minus 1 and a minimum at x equal 1. So we have to put 1 and minus 1. Then we start by drawing the arrows. From minus infinity to minus 1, the function is increasing. From minus 1 to 1, the function is decreasing. From 1 to plus infinity, it's increasing. It's increasing from minus infinity to 4. So here we put the values of x, and here we put the values of y. Minus 1, 4. Then it moved downward to 0, and then it continues to plus infinity. This is the table of variations of a function. Now, example 4, consider the function f defined on minus 2, 2 by f of x equal x squared. Show that f is decreasing on minus 2, 0. Let x1 and x2 be two real numbers on -2, 0, such that x1 is less than x2. F of x1 minus f of x2 is equal to x1 minus x2 into x1 plus x2. Since they are both negative, so f of x1 minus f of x2 is greater than or equal to 0, and then the function is decreasing on -2, 0. 2. Show that f is even, then deduce the sense of variation of f on 0, 2. The domain of definition of f is centered at 0, and f of minus x is equal to f of x. Then f is even. Since f is even and it's decreasing on -2, 0, then it's increasing on 0, 2. 3. Calculate f of -2, f of 0, and f of 2. These are the values of f of -2, f of 0, and f of 2. Set up the table of variations of f. So in this table of variations, we have to put first, on the first line, x, the domain of definition, which is -2, 2, and 0. Why? Because at 0, the sense of variations vary from decreasing to increasing. And on the second line, we put f of x, the arrows, from -2 to 0. It's decreasing, and from 0 to 2, it's increasing. And the values of f of -2, f of 0, and f of 2. Application 3. Please stop the video and try to solve the application. Thank you.